Hello, and welcome to this live webinar on introducing Dynamic CFD for buildings. My name is Nagman Khan. I'm delighted to host another EDSL webinar. Now, we've been hearing and seeing a lot about this Dynamic CFD on social and LinkedIn for a while now. It's been a few months. So I'm excited personally as well to see the launch of this product and see some live examples. Let me hand over quickly to our two speakers today and allow them to introduce themselves. Ian and Paul, welcome.
Hi,
Thank you.
yeah, Ian, obviously, one of the founders at EDSL. I've been doing this stuff for about, I think it was 37 or 38 years now. So yes, and obviously one of my interests over all of that time has been CFD and how that integrates with the building. So yeah, hopefully have some useful input on this one.
Yeah, and my name's Paul Bacon. I've worked for EDSL for over 20 years now. I joined as a chartered engineer using simulation software in the industry as a design tool. And then I came into EDSL to build and take over the consultancy department and grow and develop it from there.
Amazing. Let's take a look at the quick agenda for today. So we're going to start off with, what is CFD used for and the problems with using legacy CFD. Now, this is more of a discussion thing. We'll start that in a few seconds. Please do use the comments and Q&A section in the Teams webinar to post your opinions as well. We'll be taking some comments and questions as we go through, and we'll take the rest of them towards the end of the webinar. And then I'm going to hand over to Ian and Paul to talk us through an introduction to Dynamic CFD. There's a nice term that's new, right? A complete redesign of CFD, intrinsically linked building thermal and energy models. That sounds impressive. And then we'll take a look at some live demo and use cases, including a classroom example. That's a live demo from Ian, and an industrial warehouse and some more validation cases as well. And we'll take the rest of the Q&A. Okay, so let's jump into our discussion topic here. The problem with CFD, Ian, this has been a big bugbear of yours for decades, like you said, right? And it kind of spurred the development and the innovation around ambience or dynamic CFD. And let me just get the conversation started. Everyone we talk to, myself included, I've been using CFD, multiple other tools, desktop tools for, 20 years, ever since my PhD, the classic tools out there like, your Star CCM, your Fluent, Ansys, multiple other products out there in the market, right? A lot of people will have the same opinion of these. We've just summarized these snippets or quotes from people. This is what we hear all the time, right, Ian and Paul?
Yeah, I mean, you're quite right. It's one of the reasons I set about trying to come up with a much more stable, robust, hopefully quick piece of software that didn't have the sort of issues that are generally associated with most of the other engines which use pressure correction, which I personally think is, very, very unstable. We were using our own pressure correction for many, many years, which was, again, as I say, a good spur to get us away from that and onto something which was a better, more stable algorithm.
And the other problem with common CFD is it is just a snapshot in time. At 1 hour with a certain wind speed, a certain wind direction, you get this result. What happens the next hour? So the dynamic CFD gives you that opportunity to look at more of a full day or even longer if you wish.
Yep.
And that's quite novel because, and I think that's important because a lot of our user base and people out there, they're used to dynamic simulation or dynamic thermal modeling,
Yep.
right? When you're doing your energy thermal model. So we're used to, the hourly simulation zone by zone and looking at hourly weather data. Now we have hourly CFD, which is very interesting. And it might take people a while to get their heads around this. I think it kind of needs to be explained a few times over, right? Because you can see an animation from a steady state CFD. Doesn't mean it's dynamic. That's just an animation, right? From the steady state and static results to Paul's point. I can relate to a lot of these here. CFD takes too long and you can't deploy on every project. Absolutely.
Cost and time. Cost and time.
Yeah. Expertise as well. I think that's interesting as well, right? If you're using dynamic simulation methods, it'd be very cool to have a dynamic CFD alongside that. That, the same expertise you have from building simulation thermal modelers, who might have, building services background, energy modeling, they might have a master's degree. They could also apply dynamic CFD. That would be fantastic.
Yeah.
Right.
Yeah. And there's also the question of accuracy, because, again, we're going to see some validation stuff later, but not just linking it to the building stuff and the simulation from the building thermal energy stuff. You know, it's whether or not that CFD calculation is true, because I've certainly seen, you know, results from other CFD packages which you sort of look at and go, that looks a bit weird. So yeah,
I mean, because it's static, right? Steady state, and buildings, they're far from steady state. They're dynamic, complex behaviors, and we try and kind of capture it in, you know, a relatively simple calculation. Doesn't always work. My favorite one here, we spend ages on the building thermal energy model, and any CFD is disconnected from it. That's very true. CFD as well, you know, if you're used to sitting there watching residuals go by, and then you have to come back the next day or the weekend later, and your solution still hasn't converged, or you don't even know if it's ready to view results.
That used to really drive me mad. You'd be watching the residual plots and you're going to go, when do I stop? Because in my experience, pressure correction, you never get everything flat down to zero. I mean, it sort of goes down, but then it sort of hovers around, which is really, really frustrating.
Absolutely. And if any of these sound familiar or read familiar to you and you're watching this, you're in the right place. Let's see how we can address some of these. I'll move on to an introduction to Dynamic CFD, and I will hand over to Paul.
Okay, thank you. As I said at the start, I joined EDSL over 20 years ago in the consultancy department. And I'm just going to give you a basic overview just to show you how dynamic simulation does fit into the overall dynamic simulation that you're all very familiar with. So in TAS, we work at TAS, sorry, we work for any sort of client. We work for consultants, architects, contractors, end users. They can either be clients that have TAS of their own, but just don't have the time, or they could be people that don't want to use the TAS software and just want to outsource it all. We can take the project and put it straight into our 3D modeler tool. That's the first part where we create the geometry, and this can be brought in via DWGs, GBXML, Revit imports, lots of different ways of getting the geometry in there. But the actual TAS 3D modeler itself is a very, very quick and simple tool to use. So personally, I would much rather build a model every time. You know its integrity, you know there's no problems with it. Although we have some great, fantastic healing tools with the imports, I still prefer bringing it in straight and building it myself. From there, you can go straight away and you can start to do daylight calculations. You can do climate-based daylight modeling, average daylight factors, right to light calculations. If you want, you can then take it into the simulation engine. And there we put in the construction data, the internal gains data, natural ventilation scenarios, such as aperture openings, weather data. And then straight from that, you can do your overheating analysis. So your BB101, TM52, TM59 for domestics. We can take that into our HVAC tool and do a full TAS simulation on the systems. So we can do a component by component plant-based analysis for you. We can do all of your regulation calculations, so your Part L, your EPCs. So that is something that you're probably all very familiar with and you do on a sort of day-to-day basis. Any size project can be done in TAS, whether it be one zone through to 6,000 zone hospitals, which we've done as well before. So nothing's too big, nothing's too small. Now, the great thing about the DCFD or Dynamic CFD is that you don't have to do a great deal more once you've done all your model anyway, because all the information is in the TAS software. All you need to do is export your surface temperatures, your aperture details, and import it straight into the dynamic simulation tool that is being created. From here, you can carry on and carry out your CFD analysis. So I'll pass you back to Ian to talk a bit more about that stage of it.
Yeah, I've about to say you just stole all of my lines. I don't have much more to say on that. Yeah, I mean, the thing is the integration between the CFD and the results coming out of TAS means that and we'll be seeing this later. It's a fairly simple example, but it's just a classroom, but it will show you how fast it is to get from a TSD result or a TPD, an HVAC result, across into the CFD. The HVAC stuff is very much by hand at the moment, and certainly coming from a TSD file into the CFD is currently a consultancy offering, but you know, give it a little while, and we're certainly planning on releasing this to the user base. Good. The whole point to having a dynamic CFD tool, we've sort of covered this already. Oh, sorry, that's a lorry depot on the right-hand side, which is chugging away there. Is so that you can actually take advantage of all of that building simulation that you've done. And another benefit of having these visualizations is it's very client friendly. If you sort of show them bags of numbers or graphs, it can be good, but showing clients this kind of animation, maybe it's not so clear on that video, but it certainly helps in terms of explaining what the strategy is, why some things work, why some things don't work. So another benefit in terms of managing to get these animations out into the market. Yep. Right. I think we mentioned this earlier. Most of the other packages are based on pressure correction. So that's simple, simplex, simpler, those sorts of algorithms, which, as I say, I think not often unstable. I'd say they're guaranteed to be unstable most of the time. Yeah. So yeah, and the residual stuff we've mentioned as well. They're not terribly user-friendly packages, and I don't blame the CFD vendors for this particularly, because they're catering to sort of aeronautics, the automotive industries, lots of different industries. So the built environment tends not to get so much interest from them because it's seen as a smaller market. Yeah, not sure I'd say it's messy, but it's certainly unstable. That's for sure. Sorry, this is pressure correction. Yeah, so we initially kicked off with a 2D version of ambience, which was great, but obviously only gives you a single slice and obviously doesn't take everything into account. So the 3D version, we've been working on it for a very long time, and we've had the engine actually for at least 5 or 10 years. It's only recently that we got some decent visualization built around it, that suddenly you can see exactly what it's calculating, and it becomes a lot more apparent in terms of its power and its ability to show you what's happening inside the space rather than just giving you a single average temperature. Yeah, I think that this is deterministic and inherently stable. I think there are 5 unique features to the engine that we've developed. So yeah, lots of nice benefits in terms of stability and speed, and the fact that you've got the dynamic side to it as well. So yeah, you'll see later, you can actually just watch it, and it's relatively quick for small spaces like classrooms, but even things like atria will probably take less than a day to get a day's results out. So it's capable of doing some very useful things. It also means you suddenly not looking at just a snapshot, but you might also be looking at options. What kind of inlet diffuser do I want to use? Do we want to do this? Do we want to do that? So you can actually start to look at options in smaller spaces as well. So it actually becomes a design tool as well. So the speed thing is something that is very, very helpful. Yeah, we've been through the single moment in time and the fact that it's dynamic. Yeah, and in terms of the solar driven comfort is an interesting one, and the relationship between comfort and productivity is, I think, something we're going to be coming back onto. And once again, if you've got an existing task model and you've put the right surface information into the result file, that just gets pulled into the CFD pretty quickly, and then you just hit go, which you'll see subsequently. Yep. Yeah, and I think this has been a problem for CFD in the built environment, that it only, in my experience, it only tends to get used on the very, very sort of flagship projects, the very big buildings with lots and lots of stuff going on, or very, very critical things like laminar flow theatres, etc. Whereas parametric runs, multiple scenarios, all of that suddenly comes into view if you've got something that's very stable and quick enough, and you can run multiple options on multiple PCs, or do them sequentially. It's as I say, it's a very, very handy tool. I'm not sure the industry is quite ready to accept it yet, but that's what we're here to do, and try and convince people that this is a great piece of analysis that will really help in terms of delivering better buildings with more comfortable spaces, that will be better for the occupants and be able to spot potential issues with the current design and then improve it. And then you can show the improvement, and obviously that helps everybody in terms of making the space and the building itself a bit better. Yep, true. I'm going to show you the classroom. Sorry, I was just going to finish. If you wouldn't mind going back one. Thank you. I was just saying, typical classroom, you'll see it's pretty quick. Yeah, Atrium offices, you'll certainly do it quicker than a day. And because it's robust, stable, you don't need that sort of expertise in terms of trying to tune relaxation factors and all the stuff that most of the other packages have got. So yeah, hopefully, as I say, we're going to start designing better spaces for people at the end of the day. Thanks, Nagman. Yep. So the example I'm going to show, this was a classroom, and they were using just the top windows for CO2 control. So the concern was that when the CO2 needed to be controlled and the top windows were opening on a cold day, you'd get cold air dumping onto the kids underneath. So it took a while to find it, but I found a day where there was no heating. The main windows didn't open for cooling, but the top windows had to open for CO2. And that's the example I'm going to show shortly. And yeah, 15 minutes, yeah, you'll see. It doesn't take very long, and yeah, that was the whole point to this particular project. You know, do the kids underneath that light shelf get hammered by the cold plume coming down? Yeah, yeah, and as I say, found a point in the year. I think it was day. Yeah, we're going to see it 332 when the main windows weren't open, but the top ones were open for the CO2 control. Yeah, and this is, sorry, back one, Nagman. Last point is quite an important one. You say 5 minutes runtime for the simulation. It actually takes 15 minutes. And it's a bit frustrating because the actual CFD computation only takes 5 minutes, but the rendering takes another 5 minutes. And then if you're recording it, that takes another 5 minutes. So it's a bit irritating that, you know, the number crunching, it's pointless to do the number crunching on its own because you won't have anything at the end of the day. So you've got to record it. But the fact that rendering and then the recording pretty much triples the time is a little bit frustrating, but yeah, not a major issue. Thanks, Nagman. Sorry. Right. Let me share my screen. So I'm just firing up the software. There we go. So there's on the left side here is just a way of making little rooms for demonstration purposes, but we're going to import a TSD file. So this is the classroom. Classroom 9 is the one we're going for. Oh, sorry, I got to get to the keyboard. And down at the bottom here where I'm typing, it's 3. Can you see the cursor?
Yeah.
Somebody nod. Yeah, great. Okay, so
Yes.
day 332. I'm going to go 8 to 16. 15-minute steps and a cell size of 10 centimeters. I've did this 3 times this morning and it worked perfectly. Guaranteed it's going to go wrong now. Okay, so it's the usual sort of mouse stuff. You can spin the thing around. You can zoom in and zoom out and move it with the middle mouse button. So zoom's on the right button. I'm going to get rid of the ISO surface just to start with and just place some slices so we can see the results. So I'm trying to put the slice on. The little green blocks, by the way, are supposed to be the kids. So basically it's just the occupation gain. You can shift them around, but I'm just going to go for it. So I just lift the Z a little bit off the floor. And then if I hit go, you can see the kids warming up the air. The windows aren't open at the moment. So once the CO2 levels get going, then you'll find these windows will open up. You're seeing a bit of a cold plume coming off here. and that's only because the windows are cold comparatively. So I think it's 15 degrees outside, and as I say, it's the CO2 that they're being controlled on. This is running quite a lot slower. I've noticed this before. If you're sharing your screen on Teams, it has pretty significant detrimental effect on video performance. So yeah, normally be running quite a bit quicker than this, but it's okay. Yeah, and if you look in the top left, elapsed time is basically how many minutes or hours the simulation has run. And obviously simulation time in this case, because we started at 8 a.m. is 8:52. Now it's 53. And you'll see a bit of a pause when we get to 9 o'clock, because what the CFD software has to do is go back to the TSD file, pull the surface temperatures and the new flow rates for that particular hour, and then obviously it starts running again. You can see this cold blue plume coming down. I'll stick another, I think it was Y on it. No, wrong one. Stick another slice in there so you can see that one going as well. And that'll do. And I think not a great temperature scale, so I'm going to change the maximum to 23. Yeah, good. So now you can start to see the hot air is making its way out towards the exit. So yeah, obviously cold air is coming in at the bottom of the upper window, and it's going to be leaving towards the top. I had a list of things I wanted to do. Yeah, that's all right, done that. Oh yes, that's a good one. So I put another Y slice in here. You can see that cold air dropping off the light shelf.
And it'd be super useful just to explain the metrics on the left, because I think that's really useful for people to see what's actually happening. Yeah.
Well, as I say, the elapsed time is how much simulated time has elapsed. So we've done 2 hours 3 minutes at the moment. Simulation time is literally time of day. So this is now coming up to 10 past 10. Min temp is pretty obvious. Max temp, again, pretty obvious. Mean temp, pretty obvious. The ventilation, I think there might be a bit of a bug in that, I'll be honest with you. And mean flow, obviously, that's just the average speed basically inside the space. Frames per second, it's not doing bad actually. 10's pretty good. And you can see the sort of flows evolving. As I say, we're up at 10:30 now, so we're heading towards 11 a.m. I was going to just do a few minutes of this, but I'm going to just let it carry on if that's all right, Nagman.
Yeah. It looks great.
Well, it's almost going as fast as the bloody video, so it's a bit pointless, really.
So please, yeah, for anyone watching, please post comments or in the Q&A. Are you understanding what this is showing, right? The dynamic nature of it, and how you think about dynamic
here we go.
modeling,
Simulation
really
time is just hit 11, so all of the surface temperatures will change from 10 a.m. to 11 a.m. times. There you go. Not a massive difference, but you can see the flow rate has changed. You've now got that cold air waterfall coming down. It hung there for a second, which scared the living daylights out of me. Yeah, and there's some other display options. So you can look at contours, which is a bit, leery. There's also line integral convolution. I'm less convinced that this is actually a useful feature, and it takes an awful lot of time to compute. There you go. Always looks like Van Gogh to me. But the idea is that you've got colors to represent the temperature, and the little wiggly bits are basically showing you the local airflow pattern. I found it quite handy a couple of times. I'm going back to solid because I think that's probably about the quickest. So yeah, there you go, 11:30 coming up. And that's it really. You just sort of sit there and, you can record. So we got a button up here for recording, but as I say, if I hit that, it'll go even slower. But that just produces an MP4 line, an MP4 file. Just trying to, inlet streamlines is kind of handy, because that's sort of showing you where the air's flicking around. I mean, it's a bit too much with all the slices in there as well. Yep, so coming up to 12. Actually, let me quickly, curious to know which one's which. That's the one. No, that was not doing anything. Sorry, there's another little chimney thing here. So that's obviously not doing much at the minute. And again, you can see the windows have really opened up now. Obviously the CO2 levels, which, yeah, I can't display at the moment. I'm sorry about that. Yeah.
And Ian, just to reiterate again, the obviously the data that's being used in the CFD simulation, like the temperatures, the aperture data, the flow data, where is that coming from?
From a TSD file. So all you have, all you have to do is make sure you have the correct output specifications in your TBD. Sorry, this is the building simulation, so the modeling bit of the total building. Just make sure you've got the right surface information being produced. So that's for solids like walls, that's just temperature, and for windows, we call them apertures, that's got to be the flow rate and the temperature. And then basically that all acts as the boundary condition for these calculations, which are then, as I say, working forwards. I need to explain what, if you look in the top left here, solving domain is pretty obvious. And now you can see the windows are really fired up. So there's quite a lot more flow, obviously. That solving domain is obviously what it's doing, but there's also, I'm trying to remember what it's called now, resolving inlets. That basically means the software is trundling off to the TSD file to go and get the surface temperatures, get the aperture flow rates. Then there's resolving boundaries, and the simulation basically stops while it's doing these things. Resolving boundaries is where we're calculating the boundary conditions so that we get the right flows. Because we've eliminated pressure, our boundary condition calculation is a lot more complicated. So we can't just put face velocities in. We have to calculate another variable, which is what gives us the elimination of pressure and the robustness and stability.
Yeah, I just want to reiterate, Ian, something you said earlier. I think when you were explaining the difference between, solve time and, then you said it triples from 5 minutes, which is a bit frustrating. I think it came across as a bit, I was sitting there thinking, wow, 15 minutes, all of that's done for a whole day. That is amazing. Right.
Well, yeah.
So yes, exactly.
As I say, compared to other software, I don't think there are many other packages out there that will do this sort of dynamic analysis. So yeah, as I say, five unique features. I need to write them down at some point, but yeah, that was a few years ago. I sort of looked at the code and thought about what we were doing, and it's nice.
Ian, let's take a couple of questions on the classroom, and then we'll move on to the next case study, and then we'll come back for more Q&A later. So we've got a couple of people asking about, okay, so this is showing temperature and velocity. What other variables can we output? For example, CO2 or mean age of air, etc., etc.
Mean age of air, not at the moment, but that's on the wish list for many people. Most of these variables were for our development purposes. They're not anything anyone else is going to want to look at. We've got RH in here. That's not actually RH. That's mass fraction of water vapor, which, hang on, let me think. I think 9 will probably do it, something like that. Yeah, so kind of useless bloody temperature scale. Let's go red again. Yeah, so this is the mass fraction of water vapor in the air, which is typically, anywhere from 2 up to 10. This is actually quite damp. What we need to do, which we haven't done yet, is we can calculate the relative humidity from this once we've got the temperature to go with it. So this is the raw variable that you're dealing with, which is the amount of water in that particular bit of air. And again, water vapor is lighter. So, sorry, air with more water vapor is lighter, which means that's why you're seeing the same sort of stratification effect, also driven by the temperature to a degree.
And this is just internal room CFD right now. Someone was asking about external site. Yeah, so it's just indoor airflow simulation.
It's because we're firing it off the building simulation. So in theory, yeah, we could potentially use this technology for external flows as well. But what we do is generally building thermal analysis, which is internal. And the biggest thing about this is comfort. Again, we haven't got the metric in there yet, but PPD is one that's definitely on the list of things to do. Yeah, So once we've got the RH figured out, then we can obviously do the PPD off the back of that as well. Is that enough of that?
I think so. Yeah, it's great. Let's just summarize. So you're simulating dynamically a classroom here from 8 in the morning till 6, a whole day
We're at
in a
5
matter of
already.
minutes. Yeah. And that's CFD, it's proper full-on CFD simulation
Correct.
for a whole day, dynamic hourly in just a few minutes. That's basically the summary of this, and you're outputting, and the inputs are coming from, or rather the boundary conditions coming from your dynamic simulation
Correct.
model, right?
Yep.
For window openings, like mass flow rates and your surface temperatures, indoor temperatures, stuff like this. So it's directly linking and coupling the building thermal model now with dynamic hourly CFD,
Yes.
right? In a matter of minutes, which is the headline,
Yes.
basically, of what we're trying to communicate. Fantastic.
And
okay.
Just some other examples, which I hope you can see. So this is the lorry depot down in Dorset. They're a bit dull, these. I'm going to speed it up. And again, their concern here was that the big, large doors that you can see here and here, you get this cross flow across the space, and they were a bit worried about how cold it was going to be in there. So comfort was quite a big issue for them on that one. Can't even remember what this one is. Oh yeah, okay. This is just showing ISO surfaces. So this is just a simple room, single individual. Yeah, sorry, that's going to make people seasick. And just showing the ISO surface and the fact that you can look at sort of mid temperatures, cold temperatures, etc., etc. Sorry, that was a bit quick. Yes, this was an atrium we did many, many years ago. So I just used this as an example so I could test stuff. Yeah, so you get the idea. But it can deal with pretty much any geometry that you can throw at the building simulation, so it's not a major issue. You can see here the stepping because it's Cartesian, but I've done tests on this, and it's anyway, the validation's pretty solid.
Ian, let's take a quick question while we're on this topic, and then we'll move on to the next case study with Paul. So someone's asking about the turbulence models, how they're used and implemented.
Ooh, very good question. Very, very good question. I use KEPS. KEPS is great for turbulence, fully turbulent flows. Pretty rubbish for the built environment because the built environment is predominantly laminar, but it's, I'd say, well, no, predominantly transitional. So you get laminar bits in corners, most of it's transitional, and you get fully turbulent stuff right next to, inlet registers, high-speed stuff, or hot surfaces like radiators. You get a lot of turbulence off those as well. So again, one of the 5 unique features, we've got our own, which transitions nicely between, laminar, transitional, and fully turbulent. Which again, I don't think there's a model out there that does anything quite like that. We're quite fortunate that we don't get massively turbulent flows like, as I say, the automotive or aeronautical industry. So that's it's not quite as hard as it might seem.
And we're coming on to validation cases later, which we'll talk more about the physics in. Ian, another quick question on, is the momentum solved on the same timescale as energy? And in the classroom, the cold plume from the open window appeared to take several minutes to reach the floor. Was that just the animation? Yeah.
That's probably just the animation.
Yeah.
That basically each cell figures out the time step it should take for stability and accuracy. That's fundamentally what it's all about. So if you've got sort of dead regions of the space which are just doing very, very little, they'll be on really quite long time steps. Whereas in this example, where you've got the sort of typical Mitsubishi split system type setup, the cells right next to the outlets will be getting a lot more attention. So they'll be on a much tinier time step, possibly order of seconds. So that's the way it does it.
Okay, final question from Nuha is, what physical variable replaces pressure in enforcing mass conservation in the incompressible flow solution?
We've eliminated pressure, so that's that. But
nothing replaces it. Yeah, you've eliminated it.
Yeah. What has to happen is you lose the physical, realistic variables, and you end up with I would love to tell you all about that, but I've been told off for doing that, so I'm giving too much away. But
It's highly innovative and proprietary right now.
correct.
You must use it. Yeah, Nuha, Owen, you guys need to try it out, and we'll show you how at the end. Okay, let's move on to the next case study, Ian, and we'll take some more questions at the end.
Sorry, what case study?
The
So I'll
industrial
start this one.
warehouse. Full, yeah.
Oh, good. You're good, because I'm about done, I think. I mean, I can show you the validation stuff we've got on the website, but yeah.
We'll come back to that. Yeah.
Yeah, good. In which case, I'll stop. Oh, I've stopped sharing. Thank you. Hang on. Have I stopped sharing, or am I still going? Oh no, thanks.
Let me just skip ahead, Paul. Perfect.
Okay, so this was a consultancy project that we took on sometime last year. The client initially wanted to, it's an MOT bay warehouse that was using a lot of energy. They thought it was very leaky, and they sent us photos of the building, and you could actually see daylight through most of the joins in the building. So the doors to all of the bays open most of the day, all day, and various different configurations of opening. And they wanted to decarbonize the building, basically. So the first thing they wanted us to do was sort of do some energy calculations for them. They had all of the measured data for the energy, which was very useful in this case. So when we set up the model, like you normally would for a building of this age, those sort of constructions, it was nowhere near. It soon became apparent that it was purely down to the leakage of the building, the infiltration. So we actually modeled the infiltration in much more detailed than you would normally. We didn't just put a blanket air changes per hour in there. We actually modeled the crackage. And then we managed to start marrying up with the actual recorded energy figures that they had measured on site. After this, they wanted to work out how they could reduce their energy, because it was predominantly an air system in there. So we came up with some scenarios of scheduling doors, first of all, because most of the heat was being lost through the doors, especially being in an air system. We looked at different set points for the temperatures, and we looked at radiant systems, as you can see here. Once they found a solution that they thought they liked, that is then when we took it from the TAS model and exported it into the DCFD. And once it was into the DCFD, we could start helping to design the location of the radiant panels and looking at the temperature profiles for them. And that's when I handed this part over to Ian again, and he ran through on the DCFD software to get some of these images out that you can see here. And maybe Ian could tell you a little bit more about what he found out when he did it.
Yeah, I was just about to say that was actually one of the animations I showed just a few minutes ago. So yeah, it was an interesting example, and it's one of the most fundamental things whenever we're trying to match up the TAS results with real buildings. Most of the regulatory calculations will just give you a flat air change rate for infiltration, but actually, if you think about the way that wind affects all buildings, particularly leaky ones like this one, but all buildings, the windward side has way higher pressures, and most of the infiltration load turns up on that windward side of the building. Once the air's moved through the building and it's either been heated or cooled, there's far less load on the leeward side of the building where it's exiting. So almost every time, that's the first thing you have to do to try and get close to real building performance. The other thing as well is real buildings have far greater thermal bridging and edge loss effects. So again, you just have to change your sort of regulatory type model to account for all of these actual real world imperfections. I always think of the regulations as, you know, it's a perfect target because it's perfectly built, perfectly constructed, perfectly occupied, and the plant works perfectly as well. Whereas once you get to a real building in real life, God, everything's wrong. Well, not everything, but yeah, that's where these massive discrepancies come from. Yeah. Sorry, went off topic a bit there.
I think that's all there is to say about that.
Yeah, yeah. No, I was just about to say that the guys who did the work, actually, this is a good point to talk about it. They did an awful lot of work as well with different design strategies. I think they have batteries on this one, Paul. I think
they had batteries. They also had PV, and we sized the PV for them so that they become carbon neutral at the end of it when they got their new heating system in.
Yeah. So again, sorry, I think this is you and I, Paul.
Yeah, we got some raving reviews from them afterwards, didn't we? They were very happy with what we did. They put the full report together, and they couldn't speak highly enough of us for the work we did.
Yeah, and it was an interesting design because it wasn't just about infiltration CFD. They had some very interesting, as I say, I think battery stuff, PV stuff, and did they eventually get to be carbon neutral? I mean, was it zero?
Well, yeah, we put enough PV on the building in the end to get it down to carbon neutral, but the actual energy dropped significantly just by changing the heating systems from the work we did.
Okay, yeah, that makes sense.
Amazing. Let's go on to validation because there are a lot of questions about, especially from the CFD users, right? They're super interested in this very innovative technology that's been developed here, Ian.
Yep.
And from anyone who knows anything about CFD, if you haven't read validation cases, you don't know what you're talking about. So from the academic literature.
Yeah. We're going to post this PPT online, aren't we, and send everybody the link?
Yes, exactly. Yeah.
Great. In which case, I'll be honest with you, I could probably do a whole talk on just the validation exercises, but I'll tell you what each of them roughly means. The displacement ventilation experiments were done by Marcel Lumens, and this was like an office with a single occupant, 2 PCs, chair and table, and obviously he did the full experiment, which was brilliant, and that's actually the pictures of our simulation on the right hand side. And we managed to match up quite nicely with his sort of qualitative results, which is great. So that the images you can see on the left hand side there are basically what he was drawing in his work as the sort of experimental results. So all these links are worth chasing down and reading. As I say, you could easily fill another presentation with just this stuff. Experimental validation was done at Cranfield. They built some test cells, which aren't great because they're very lightweight, but they were basically looking at the difference between single glazing. Oh no, sorry, it was to do with response of fabrics. Sorry, that was another experimental validation. No, this was to do with response of the building, and I think it was BRE and somebody else and ourselves who put that together. And again, we got some very nice results from that one. The actual space had loads and loads of sensors, so it was a perfect example in terms of matching up CFD with real world performance. Jet nozzle comparisons, that's basically Krantz and Waterloo. They make these jet nozzles and effectively they put them in these massive hangers, turn them on full blast, and then look at the velocity decay through the center of the jet. We did exactly the same thing with the CFD, and I must admit, I looked at it just the other day, and the comparison between what we're simulating, what the two different manufacturers were measuring is quite incredible. So that's a nice one. Scaling and grid independence. This is a classic problem for other CFD packages. Excuse me. If you change the grid or change its density, you quite often get very different results. So that's a series of tests on a small cube, which is basically three different mesh densities, exactly the same physical size, but very different model sizes. And the agreement again is nice. So that's very good. Time accuracy verification. I think this was a cube. We kicked it off, I think, at 30 degrees for the air inside the space, and the boundaries were at 21. And then obviously over time, you should see that 30 degrees decay down towards 21. ASHRAE, I think, no, it wasn't ASHRAE. Analytical solution. So yeah, there's an analytical solution, then we did a stirred solution for the CFD, then we did a sort of normal solution for the CFD, and the difference in the three results is interesting. The stirred CFD is obviously a lot closer to the analytical solution, but the naturally, convecting one obviously decays a lot slower. I think the additional validation examples are the classic backward facing step, which is a very, very common CFD exercise. There's also the hot plate, which is just blowing air over a hot plate and seeing how much heat's picked up by it. So the heat transfer coefficient test effectively. And the final one, I think, is differentially heated cavity. So this is like hot on one side, and cold on the other, and obviously you get the nice, the normal sort of convection patterns. And again, we're matching up with experimental data quite nicely on that one from memory. But yeah, it's well worth a look. Yeah, all of those are well worth a look.
Okay, brilliant. So there's plenty of validation really to show the assumptions you made and the technology that's been developed works, right? Especially in the built environment and the kind of cases that we come up against in, in buildings and HVAC and thermal comfort, ventilation, that vent, yeah.
Yeah, it's why I said we're not one of these generic CFD packages, because they're doing stuff like, if aeronautics, you've got to worry about, shock waves and all sorts of weird stuff. So, the built environment is challenging because somebody asked, laminar transitional fully turbulent is not an easy problem to solve, but we don't have the crazy stuff. We don't have the massive high speeds, as I say, shock waves, that kind of stuff. We don't need to concern ourselves with.
Okay, let's move on to the next section, which is, Ian, how do people start using Dynamic CFD on their projects? What's the best way to go about this? I'll hand over to both of you.
At the moment, it's purely a consultancy tool. So if you are a TAS user and you have a TAS model, all we'd really need is the T3D and the TBD files, and then we could quote you very quickly and easily for space analysis through a day. Again, if you're not a TAS user, then Paul will quite happily put a model together for you.
So from any consultancy project, we work on a bespoke basis. We will price every job individually. We don't have a flat fee. So like Ian said, if you've got a TAS model already, send us a TAS model and then we'll let you know how much it will cost to run the DCFD. If you don't have a TAS model, we're more than happy to create a TAS model for you and do that part on your behalf and then run the DCFD. So we can do it however you want to do it, whichever works best for you.
Yeah.
At the moment, as I said at the beginning, we will carry out all of the compliance calcs, overheating calcs. So this is just quite a very simple bolt-on at the end, which is the great thing about this software. There's no extra work to be done really. The majority of it's all there. It's just a matter of running the calculations at the end. So it's going to be a game changer. I think a lot of people are going to find it as more of a design tool now rather than just something fancy to show their clients at the end. So it should help to make the environments more thermally comfortable for everybody. So I think we'll see a change in the way that people start to design buildings because of this.
Great. Yeah. I mean, it's a great way to. Yeah, go on, Ian. Sorry.
Sorry, I was just about to mention the link between comfort and productivity is huge. When we were doing the work at One New Change for Land Securities, I was fascinated because we managed to save, I think, £50,000 to £100,000 per annum just by changing some of the HVAC settings. But if you actually look at how comfortable people are and how that affects their productivity, you're talking millions. I appreciate the salaries in London are crazy, but if you can make somebody just 2 or 3% more productive, or all of the people in a building, the money is massive. It's absolutely huge. So I think that's another nice aspect with the CFD, because you can actually say where you're going to have comfort issues, etc., etc.
Yeah. Great segue into some Q&A. Actually, we've had some people asking about that. So I'm going to jump in. Please post any final questions, comments in the chat now, and we'll get through as many as we can. So Ian, we have some people asking about, sorry, let me just read this. So you already answered about how to access this, right? Mm-hmm. The Dynamic CFD.
Yeah, just consultancy at the moment. That's it. We have to do it. Yeah.
And you mentioned Cartesian grid. Why just a Cartesian grid?
Speed. And also, people always go on about that. We're all staring at a 2D Cartesian grid. It's called a screen, each pixel. And this was my idea way back, was each cell just becomes like a pixel. And we're getting very close to that now. That classroom is a little way off, but if you wanted to spend 3 hours on it rather than 15 minutes, you could run a much finer grid and you would almost be down to pixel definition. Yeah. So that's the reason for it.
Yeah. Okay, I'm going to cluster a few questions because they're quite similar. You're going to love this, Ian. So when is Insta3D coming out? When can users actually start using it and trialing it out? And what tiers are there? I mean, imagine there's a beta, perhaps a general release much later. Is there some early access program for TAS users?
There will certainly be an early access program. The quick answer to when will we release it is when it's ready, is the quick answer to that. It's probably ready now for NatVent stuff, but I'd still like to do some more testing. The tricky stuff is the HVAC side of things. Inlets and outlets, as we call them, sorry, supply and extract grills, whatever, placing them, setting them up, all that kind of stuff. That's the trickier bit, and the controls that go with that. That's why we're desperate for consultancy work, I'll be honest with you, not for the money, but to drive the development of the software. Because guess what, you know, if people have got problems that this might solve, then those problems are going to be occurring with other companies. So that's what we're after.
Talking of problems, Alex is asking about unique shapes like a dome or an oblong dome, which I know Andrew worked on something like that as well. So how good is the CFD on shapes like that?
It's absolutely fine, because basically it just fills it up like a bunch of cubes. So this is the simplicity of it, and yeah, people are going to go, hang on a minute, you've got a jaggy surface running across there. I've actually done experiments on this, and the dome results were absolutely phenomenal. Probably a sample I should have thrown into this, you know, presentation, but because we're fifth order in terms of you know, we don't just look at the cell and the 4 cells around it. We look at a cluster of, this is in 2D, we look at a cluster of 9 cells plus 4 cells further out, which means all of these complicated shapes become very smooth. So I've done jets at 45 degrees, which in typical CFD package, you get a thing called false diffusion, which means the air is very happy to go in the X direction, it's very happy to go in the Y direction, but if you want to go at 45 degrees, it suddenly acts like glue. And the dome was amazing. It was absolutely circles within circles within circles. Even I was expecting to see some sort of distortion, but it was absolutely perfectly circular. I should have put this into the presentation, sorry.
Well, we can share it in the follow-up email. That'll be good in a couple of those images.
Remind me.
Here's a good way to end. Here's a good question for Paul, really, on the users who have live projects, whether it's classroom or warehouses or offices, and they're looking to use or try out this technology. What's the action, Paul? What do you need from them, really, to get a quote, whether they have a task model or not?
Yeah, okay. So if you contact either myself direct, Paul at edsl.net, or come through to consultancy at edsl.net, if you let us know your requirements, so if you have a task model of a school, for example, and there's one classroom you want us to carry the calcs out on, just let us know which room that is, and we will carry out the rest for you. We'll let you know how long and how much it's going to cost, and we will go from there. If you don't have that task model, send us some CAD drawings and we'll create that classroom for you and do that for you. But at the moment, it is just consultancy, as we've said. But hopefully next year you'll all be able to do this yourself. So buy TAS now and get learning. And
there goes the sales pitch. Well done, Paul.
Yeah, it's from what I've been told, it is a relatively cheap package to run anyway compared to others out there. So jump on, have a look, and get using it.
Yeah, and we are undecided at the moment about costs, etc., etc. So certainly, if you're an existing TAS customer, you're going to get preferential treatment in terms of getting access to this. Yeah, but yeah, the fundamental thing is, you know, this will probably drive TAS sales more than we're interested in earning money out of the CFD.
Okay, I think we're done. It's great. We're top of the hour now. Fantastic.
I think the last slide talked about the TAS prices as well, didn't it? If people did want to have a look and if they wanted to purchase it, so they could get familiar with TAS before they start using the CFD.
Yep. Yeah, and in fact, you know, as you rightly say, Paul, good idea to get stuck in. I mean, the prices are crazy. They're probably going to be going up, so get in quick. But yeah, once you've got the TAS model sorted out, then yeah, tacking the CFD on the back end of it really isn't going to be that much of a chore.
Great. Let's finish there. Thanks so much for joining, everyone. Ian, I'll hand over to you for some closing remarks, and we can end the webinar. Thank you.
My closing remarks are, oh my God, I'm really glad that's over, because it was quite nerve-wracking this morning. Doing live things, you know, it's much easier just to flick through a PowerPoint or yeah, just play a video. But no, it's good. I got good feedback the last time I did it live, because I hope it's more interesting for the audience, because they can actually see what's going on and how everything works. So yeah, all good. I can go and relax. I might even treat myself to an early beer.
Thanks, everyone. We'll end the webinar there. Thank you for joining, and you will receive a copy of the slides and the recording in a couple of days. Thank you.
Lovely stuff.
Thank you.
Cheers, guys.